In many occasions, professors like to bring some tricky questions in their exams. In this presentation, we are going to discuss one of these problems in Reinforced Concrete Design 1. This is our example, and here we have the yield stress of steel is 60 ksi, and the compressive strength of concrete is a 3.5 ksi. The beam cross-section and its reinforcement are all given. The area of the compression steel is 2 square inch, and the area of tension steel is 3.81 square inch. The stress-strain response or stress-strain behavior of concrete is also given. Notice that the stress-strain response consists of two parts. The first part is when the concrete behaves in an elastic manner up to a specific point, and this specific point is 0.9 F'C in stress and 0.002 in strain. Beyond this point, the concrete behaves perfectly plastic. This is different from what we used to see in this topic. Therefore, most of the equations found in the textbooks on RC1 cannot be used directly. Here I mean Whitney stress block cannot be used. In our solution, let's assume that the tension steel will yield. In other words, the strain is greater than 0.00207. The question now, how to get around this problem? The answer is use strain and stress distribution along the cross-section of the member. Notice that the strain distribution is based on sections perpendicular to the axis of bending that are plane before bending remain plane after bending, while the stress distribution is based on the stress-strain response given in the problem. The stress distribution consists of four parts. 1. When the concrete behaves perfectly plastic with unknown depth of K, and K is measured from the top fiber of the cross-section. 2. When the concrete behaves in an elastic manner up to strain 0.002, and the distance in this case will be C minus K. Notice that both C and K are unknown. 3. Compression steel at the level of strain 0.0015. And finally, tension steel at distance D measured from the compression face or the top face of the cross-section. Since the sum of the forces in the x direction must be equal to 0, then AS times Fy, this term represents the force in the tension steel, must be equal to AS prime times epsilon S prime times ES. This term represents the force in the compression steel plus 0.9 times F prime C times K times B. This term represents the force in the concrete when the concrete behaves perfectly plastic plus 1/2 times C minus K times 0.9 times F prime of C times B. And this term represents the force in the concrete when the concrete behaves in an elastic manner, where AS is the area of tension steel, Fy is the yield stress of the reinforcing steel, AS prime is the area of compression steel, epsilon S prime is the strain in the compression steel, K is the distance measured from the top fiber of the cross-section to the point where concrete starts the plastic behavior, F'C is the compressive strength of concrete, Es is the modulus of elasticity of steel, B is the width of the cross-section, and C is the distance measured from the top fiber of the cross-section to the neutral axis. If we substitute for these values, simplify the results, and rearrange the terms, we will get equation 1. Notice that there are two unknowns in equation 1, C and K, and our goal becomes finding these two unknowns. The second equation can be obtained from the concept of similar triangles. The first triangle is alpha, psi, lambda, and the second triangle is alpha, beta, eta. Notice that both triangles have the same tangent. Therefore, 0.002 over C minus K should equal to 0.0015 over C minus 2.5. 2.5, this number, represents d prime. Now, if we simplify this equation, we can get equation 2. Solving equation 1 and equation 2 simultaneously, we can get both C and K. It turns out that C should be equal to 4.631 inches and K should be equal to 1.791 inch. Calculate the concrete compressive strain on the top surface of the beam. Here we're going to use the similar concept, the concept of similar triangles. But this time we're going to use this triangle and this triangle. Or we can use this triangle and this triangle. If we do so, we will get epsilon C over C must be equal to epsilon S prime over C minus d prime. Now, if we substitute for these values, we will get the compressive or the concrete compressive strain at the top surface of the beam, epsilon C. It turns out that this value is equal to 0.00326. Or we can use this equation. Epsilon C over C must be equal to 0.002 over C minus K. Calculate the steel tensile strain. Again, we're going to use the same concept, the concept of similar triangles, but this time we're going to use different triangles. The first triangle will be this one, and the second triangle will be this one. Notice that both triangles have the same tangent. Therefore, epsilon c over c must be equal to epsilon s over d minus c. If we substitute for these values, we can get the tensile strain in the tension steel. The strain in the tension steel turns out to be 0.0119, and this value is greater than 0.005. Therefore, the section is tension controlled. Calculate the modulus of elasticity of the concrete in the elastic region. We know that the modulus of elasticity is a stress over strain. The stress is 0.9 f prime c and epsilon c is 0.002. Now we can calculate EC. The modulus of elasticity of concrete turns out to be 1,575 ksi. Finally, calculate the moment capacity of the cross-section. Summing the moments about the neutral axis, we will get Mn equals 0.9 times f prime c times b times k times c minus k over 2. The term c minus k over 2 is the moment arm, plus 1/2 EC epsilon c in the elastic range times b times 2/3 times c minus k squared. Two things are worth mentioning here. The first one, the term EC times epsilon c in the elastic range should be equal to 0.9 f prime c, and the moment arm is 2/3 times c minus k plus as prime epsilon s prime es times c minus d prime. The term c minus d prime is the moment arm, plus as times fy times d minus c. Again, d minus c is the moment arm. Now, if we substitute for all these values, we will get the nominal moment capacity. The nominal moment capacity turns out to be 4,455.25 kips inch, or 371.27 kips foot. The design moment, or the factored moment, is nothing but 0.9 times 371.27. The result will be 334.144 kips foot. The reason behind using a reduction factor of 0.9 because the section is tension controlled.